Thank you, we're live. Today I'm going to show a very classic proof by contradiction that you might have your first exposure to, aside from this irrationality of the square root of 2, of a proof by contradiction, which is the proof that there are infinitely many primes. And these are structured as two exercises taken off from Gallien's 9th edition of contemporary abstract algebra. But you could go this through any number theory or even like an IB/HO math class if need be, going for the analysis and approaches. So how do we prove that there are infinitely many primes? Well, suppose to the contrary that there are a finite number of primes, and we can list them out. So this list would include P1, as stated over here, P1, P2, P3, Pn-1, this is just arbitrary how much I'm listing it, up to Pn. And now we're going to create some arbitrary, bizarre new quantity. We're going to take all the finite primes that we consider exist in this universe and multiply them together, slap them together like that. Except with one caveat, we're going to plus it by 1. Now, we want to show that this expression here is divisible by none of these primes. The fundamental theorem of arithmetic says every integer greater than 1 is either a prime number or it can be factored into a product of primes. That's kind of like seems easy, and it could be formally written out, but for the sake of saving time, I'm not going to do that because my word processor might give a bunch of errors here. So we have two cases. The number generated by here, all the numbers in the universe can be prime or composite, correct? You either have prime or composite. Well, what if the number generated by here is a prime? Then we're seriously into a problem, because then we just generated a new prime that was not originally in our list of n primes listed here, finite. So that's a contradiction, and we run into a problem. On the other hand, if P is composite, then there is at least one prime that divides the list. And this is basically an application of Euclid's lemma, which you might show to prove that the square root of 2 is irrational. So any ith prime within this list from the first to the nth prime will divide this big, giant, nasty expression here. And it will also divide the product of the primes, naturally. But then we can say that the ith prime equals some multiple of any arbitrary integer k1 equals this. And that's the same with the product. It's any other arbitrary integer k2 multiplied by these primes together. If I carefully subtract these quantities together, I will end up with, on the right hand side, just two different primes being subtracted with each other with a common factor of pi. And we don't care really what this integer is, except that it is an integer. But what happens to the ugly expression and the product of the primes? Well, the product of the primes, they just cancel, and you end up with 1. Therefore, you have to claim that every single prime has to divide into 1, which is nonsense. That does not work in general for any examples at all. 1 does not divide into any prime. For example, 1 does not divide... any prime does not divide into 1. For example, 3 does not divide into 1. If you divide 1 over 3, that's, well, just 1 over 3. That's a rational number or a fraction. Fraction. Not an integer. So we have a contradiction, and as a result of that, there are an infinite number of primes in total. And that's QED. End of the proof.